Alrighty, folks. So moving along here now into, believe it or not, our second last unit, trigonometry. So 3 units done, 2 more to go. We're going to start trigonometry in this lesson here. It's a longer unit. There's 5 lessons in it. But yeah, we'll get a start on it here. We're going to be looking at a little reminder of angles in standard position from Math 20, introducing some new ways to think about angles and some new ways we can calculate some quantities with them. So as always, there's the big ideas, the main skills we want to be able to walk away from the lesson with. So use that as a little checklist at the end to, check in with yourself. All right, let's get going. So like I said, we'll start out with a little review here of Math 20, the trigonometry we did back then. Specifically, we're going to start out with angles in standard position and what that means, okay? So before we talk about that, let's just remind ourselves of really what is an angle. I mean, if we really boil it down, an angle is just a way of describing the positioning of two lines relative to each other, right? At the end of the day, that's what an angle's about, okay? Or two, positions relative to each other, typically lines. So for example, right, this is a 10-degree angle. Could make it bigger and talk about the 45-degree angle here. Note that you could also go around the other way and talk about a, 360 minus 45 or 315-degree angles, because 360 would be the full circle, right? That's one way to describe it. A 90-degree angle here, a 120-degree angle here, right? As we make it larger, we get a bigger angle. And so that's all an angle in standard position is doing. It's just that our two lines are made by what we call an initial arm and a terminal arm. Initial and terminal kind of gives you some clues there, right? Initial is where it starts, its initial position. Terminal is where we think of as the angle ending, as we kind of create it, right? So that is what we're doing with angles in standard position. They are what we call rotation angles. So we're essentially imagining, okay, if I started from here and I rotated to here, what angle would I be rotating through? So for this one, that's a 45-degree angle, right? If I started at this position and I rotated through to that position, I've rotated through a 10-degree angle, 90-degree angle, 120-degree angle, etc. Okay, so they're rotation angles, and don't forget, for us in trigonometry, these are all happening for an angle in standard position on the Cartesian plane. Cartesian plane being what you know and love. This is the Cartesian plane, the x and y axes, right? So we're just rotating around the origin there. So the angle is, we kind of say it's swept out, so to speak, between two positions known as its initial arm and its terminal arm. So it starts at the initial, that's why we call it initial, and it terminates at the terminal arm, hence the names. We say the rotation is positive when it's counterclockwise, and it's negative if we rotate clockwise. Okay, so just for an example, we could make a angle in standard position. We could rotate from the terminal arm, the initial arm here. We could rotate, positive 120 degrees, and that would be counterclockwise, so it's positive, right, to create our angle. Rotating through that would be my initial arm, and that would be my terminal arm. And I rotated counterclockwise 120 degrees. So that's a positive angle in standard position. We could have also gone, right? We could also start from the initial arm here and go negative 240. That actually gets our terminal arm into the same place, right? Okay, why negative? Because I rotated clockwise there. Okay, clockwise there. So that's just a couple examples of angles in standard position. One positive, one negative. Just some, standards and conventions for when we're dealing with angles in standard position. The initial arm always starts out on the positive x-axis. So it's always like what I drew there. It's sitting pointing to the right on the x-axis, okay, the positive x-axis. And we're always going to start rotating from there for an angle in standard position. The rotation's always happening around the origin, 0, 0. So it's never going to be like rotated around here or here. The center here is always kind of the middle of our rotation. The terminal arm just shows us where that rotation ends. It's, where the angle is. So the angle is the angle between the initial arm and the terminal arm. Essentially what we're doing here is thinking about the angle we would have to rotate through to go from the initial arm to the terminal arm, right? So just to give an example and a non-example, here's an angle in standard position. The initial arm is on the positive x-axis, the terminal arm's here. We've rotated counterclockwise, so this would be a positive angle to get to here, right? This is a non-standard position angle. It's still an angle we could think about. We could think about rotating from here to here, but it's considered non-standard position because, do you see why? The initial arm is not starting on the positive x-axis, right? Another non-standard angle would be something like if you had your initial arm like this and you rotated, to there. Why is this considered a non-standard angle? Because it's not centered about the origin, right? So just to quickly show what we're doing here, right? There's a lot of stuff going on here. A lot of this stuff we will talk about in this unit, but just right now using it to think about the rotation angles, right? See that there? I'm rotating, and what it's showing me, I'll put in a label. There's more labels than we need, but do you see that label there? Theta, that Greek letter theta that stands in for angles. It's showing me the rotation angle, okay? And that's what we're doing. We're creating that angle by rotating and thinking about where our terminal arm ends up. Notice on the left-hand side of the page there, I can't really point, but do you see the angle getting larger as I rotate further and further, right? Once I make a full 360 all the way around, the angle's 360. If I go all the way around twice, 720, backtracking a bit, right? 90, 180, 270, 360, okay? Watch what happens if I go the other direction. See on the left side there, the angles now become negative. It's still an angle in standard position, but because that rotation is clockwise, we define that as a negative angle. Okay. So let's do a little warm-up from stuff we talked about in Math 20, okay? We're going to do some labeling, remind ourselves of the vocabulary and stuff here that we need to have with us as we embark on our trigonometry journey. So we want to label the angle that's in standard position to the right with the following. The terminal arm. So that's where it ends, okay? We've got two arms there. I see two arms. Which one's initial? Which one's terminal? Right? This one is initial because initial always starts on the positive x-axis. Right? This is the x-axis, this is the y-axis. Okay, the terminal arm, that's where the angle finishes. It terminates. That's the terminal arm. So we always imagine starting here and rotating to create our angle, right? Counterclockwise if positive. Typically, they'll be positive. We will get negative ones thrown at us every now and then. Okay, the angle theta that's suggested by these arms. Well, starting from the initial arm, we're going to rotate that far. And whatever angle we've rotated through, that is our angle theta. Greek letter, theta. Okay, quadrants 1, 2, 3, and 4. Well, this is why they have the numbers quadrant 1, 2, 3, and 4, because if we're rotating in the positive direction, we start here and we rotate through this quadrant first, this one second, this one third, this one fourth, before we start repeating ourselves, right? So this is quadrant 1. This is quadrant 2. This is quadrant 3, and this is quadrant 4. It's most common to use Roman numerals for those. Of course, it's okay to just use regular Arabic numerals as well. And sometimes you'll see Q put in, just saying Q for quadrant 1, 2, 3, 4. Okay, so always 1, 2, 3, 4. All right, and we want to label 0 degrees, 90, 180, 270, and 360. So count it out with me. If we haven't rotated at all, we've gone through 0 degrees, so this is 0 degrees, right? The positive x-axis is 0 degrees. Rotate to make a 90-degree angle, right? Perpendicular. This is a 90 here. Keep going another 90-degree angle, right? So now we've gone 0, 90, we're at 180. So this is 180 degrees. Keep going another 90 to get to the negative y-axis here. Another 90, well, 180 plus 90, we've now gone 270. And if we keep going another 90, we've gotten to 360. We've done a full circle, right? If you do a 360, that means you've done a full spin. Okay, so notice 0 and 360 are actually in the same place. We'll learn eventually that these are called coterminal, meaning that their terminal arms are actually in the same spot. And the characteristics of coterminal angles are, well, they have all the same features, except obviously one involves more rotation than the other. Okay, So there we go. Little reminder of that terminology. The initial arm, the terminal arm, the angles, the symbology we use, the quadrants, and all that good stuff. And we actually call these angles 0, 90, 180, 270, and sometimes 360 gets lumped in there as well. We call them the quadrantal angles because they are what separates one quadrant from the next, right? Between 0 and 90, you're in quadrant 1, but as soon as you pass 90, you're now in quadrant 2. And then once you pass 180, quadrant 3, right? They separate the quadrants, so we call those the quadrantal angles. Okay, now it wants us to sketch each angle theta in standard position. So I'm just going to remind ourselves, we got 0, 90, 180, 270. Could also think of 0 as 360. If we go all the way around, we're back to where we started. Okay, so let's draw out a 145-degree angle, right? We can draw in our initial arm, and starting from there, starting from the positive x-axis, we're going to start rotating. Now, 145, right, if we think about it, we need to go past 90, but not quite all the way to 180, right? So past 90, in fact, we can say we need to go about 55 degrees past 90, which is a little more than halfway to 180, because again, another 45 degrees would be halfway to 180, right? There's 90 degrees here total. So we're just sketching. It doesn't need to be perfect or anything, but just making it a little bit past halfway to 180 from 90, right? So past 90 and then about 55 more degrees to get to an angle of 145. And there we go. We've sketched out our theta, our angle. Okay, theta equals negative 215. So here's 0, here's 90, here's 180, here's 270. But something to think about here, yeah, that's 270. But do you see how we could also think of it as negative 90, right? And this as negative 180, and this as negative 270, right? Do you see how those are kind of the same thing? Because if I rotate in the negative direction, that's clockwise. So let's just start doing that. Okay, there's my initial arm. If I start rotating in the negative direction, well, I've just gone through 90 degrees there, right? That's negative 90 degrees in standard position. So I need to go past negative 180, but not quite all the way to negative 270, right? In fact, I only want to go, 35 degrees past negative 180. Hey, these are actually coterminal angles. The first two that we just did, A and B, right? Because if you think about it, this is negative 215. It's actually ending in the same spot as this one. This is 35 degrees away from 180. So is this one, right? So their terminal arms are actually in the same place. We'll talk about coterminal angles more in this unit. But there we go. We sketched out an angle in standard position of negative 215 degrees. Here's the next one, 325, positive. So I'm going to rotate counterclockwise from my initial arm. Starting at 0 degrees, I'm going to go past 90, past 180, even past 270, but not all the way to 360, right? We're stopping at 325. So 270 to 325, I'm going about 55 degrees past 270, which means it's a little more than halfway to 360 from 270, something like that, right? And so there is an angle of 325 degrees, okay? Pop quiz, what quadrant is that? That's in quadrant 4, right? We're terminating in quadrant 4. These two were both in quadrant 2. Okay, let's talk about radians now. We've done our quick little review of, the basics of the angles in standard position from Math 20. Let's introduce something new here, okay? Radians. So radians, sometimes students really don't like these at first, okay? And I get it, they look kind of weird. There's a pi and all that stuff. But I want you to just, right off the bat, at the beginning here, we just got to understand that these are just another way to measure an angle, Okay, it's exactly how like you could measure a distance in meters or in feet, right? I mean, most of us, when we're asked our height, we say something in feet and inches, right? Like I'm 5 foot 10 inches. But like on your driver's license, for most of you, if you have one, it's going to say it in centimeters, because in Canada we technically use the metric system, right? Those are both measuring the same thing. They're both measuring your height, and they mean the same thing. They're just expressed differently. So just like we can measure a distance in meters or centimeters or feet or inches, but they're all talking about the same thing. They're all talking about how long or how tall something is, right? There are other units. That's what those are. Meat feeders, feet, meters, centimeters, inches. They're all just units, different ways to measure a length, okay? There's other ways to measure angles besides just degrees. So most of your math courses until now, in fact, all of them until now, have used degrees to measure angles, okay? But there is another one, and it's honestly a lot more like natural and intuitive, and it's been around for a very long time. And students don't like it at first because they're so used to degrees, but I promise once you get used to them, they're actually a great way and a very like natural way to think about angles. That's why they've been around for so long, is even like ancient mathematicians looked at circles and they said, hey, we should measure angles like this. Okay, so that is all a radian is. It's another way of measuring a angle. Okay, if someone gave you their height in centimeters, it's not like you would think they were weird or anything, right? You might say, okay, I need feet and inches to really think about it, but you would know that they was valid, right? Same thing here. Radians are just another way of measuring angles, just like degrees. So a radian, sometimes we call it a rad for short, or we use like rad as like a unit. It's the where it comes from, the definition of the radian, and this is why it's such an intuitive way to think about circles and angles, is it's the angle that is made in order to sweep a distance around the circle's circumference that is equal to that circle's radius. So what I'm saying there is, notice like whenever we're making these rotation angles, right? If I go back to this one, you can imagine that as I make a rotation angle, I'm sweeping out along, if you watch that red dot, right? If you watch that red dot as I rotate, here, this red dot up here, okay? Notice that I'm kind of sweeping out along the circle's circumference, along its border there, right? Imagine that red dot was a paintbrush. I'd be painting out a certain section of the circle's circumference. Okay, now what a radian is, what the angle is for a radian, it's just the angle that we would have to move through in order to sweep out along the circle's circumference exactly one radius of the circle. So notice my arm here, my initial arm is just, it's being like it's one radius of this circle. So once I've swept out that distance, I've traveled one radian. You know, roughly there, maybe a little bit behind. Okay, so these diagrams are showing that here. That's all a radian is. It's an angle. It's specifically the angle that we would need to rotate through so that this distance here along the circle's circumference that we've swept out, we say subtends is the fancy word, or is the proper word, I should say, for sweeping out. Sweep is like subtend. That's the proper term. Okay. We've subtended an arc along the circumference of the circle that is exactly one radius long. So this here and this here are equal, making the angle that we've moved through here, by definition, one radian. Okay, and that's why this kind of came up naturally. As they said, well, the circle has a radius, so how do we want to think about angles? Well, why don't we think about how far you would have to rotate through to make one radius along the circle's edge? And again, you might say, well, this is weird, but you're used to degrees. What's so great about degrees, right? I mean, 1 degree is 1/360th of a circle around, right? There's nothing super intuitive about that. The reason we use it, honestly, is just that 360 is nicely divisible. It can be divided by so much stuff, right? This is actually a lot more natural. Why 1/360th of a circle is going to be the definition of your angle measure, right? Why not make it one radius the angle you'd have to move through to subtend 1 radius, right? It kind of makes sense. Okay, it'll take a little getting used to, I get that, but just trying to convince you that it's nothing to be scared of, it's just another way of measuring angles. We'll see why it's such a nice way in a second here too, right? So this angle is 1 radian, there's a radius, right? And that means that we have subtended an arc of 1 radius along the circumference of the circle. So by definition, this angle theta is 1 radian. And so now we get into the kicker of why radians are nice to work with. Because the fact that a radian subtends an arc equal to the radius of the circle, the arc is this thing, what we've traveled along the edge of the circle while sweeping out our angle, okay? The fact that the radian subtends an arc of 1 radius makes radians a super intuitive way to measure angles once we get used to them. And this is because the circumference of a circle, circumference, remember, that's like perimeter for a circle. It's the total distance around the circle. How far would you have to move if you walked all the way around this circle? That's its circumference. And the way we calculate the circumference, if you think back to your previous geometry, is that the circumference is just 2 pi times the radius. Okay, it's 2 pi times its radius. So how many of these radii would fit if we were to go all the way around the circle? Well, 2 pi of them, right? Now, I know that seems a bit weird, 2 pi, but remember, pi is just a number. So it's about, pi is 3.14, so 2 pi is about 6.28. So about 6.28 radii will go around the entire circumference of a circle. We don't say that. We don't say 6.28 because why bother? We've got a more accurate, unrounded way. We can just say 2 pi. So what that means is that if 1 radian angle subtends or sweeps out 1 radius, then that just means a full rotation in radians is just 2 pi radians, right? If 1 radian sweeps out 1 radius and 2 pi radii fit into the whole circle, well, then we have to rotate through 2 pi radians to make a full circle. So instead of saying 360 degrees, we could also say that a full circle is 2 pi radians, right? It's just like saying, instead of saying 5'10", you could say you're 175 centimeters. Those mean the same thing, they're just being measured differently. So 360 degrees is a full circle, or 2 pi radians. And then a half rotation is going to be, well, half of 2 pi, or 1 pi. So we could call it 180 degrees, or we could call it pi radians. And then a quarter rotation, 90 degrees, that's going to be, half of a full circle, right? So half of pi, or pi over 2 radians. 3/4 of a rotation, that's 270, that's 3 times 90, right? If a quarter rotation is pi over 2, then 3/4 rotations is 3 pi over 2 radians. And this is the nice thing about radians, is we can think of tons of these angles, right, especially like our quadrantal angles, as just being like the fraction of 2 pi that they represent, right? And again, I know you're saying, come on, I had no problems with 90, 180, 270, 360. Why are we mixing in this new stuff, okay? Honestly, if you study math, like if you ask a math professor for an angle, they're not going to give you an answer in degrees. They're going to give you an answer in radians, because once you get used to them, they are a much more intuitive way to work with angles, and they let us get like exact values without rounding and without having to think about 1/360th of a full rotation. We can just think about the fraction of 2 pi that our rotation represents. So using radians, radians are so handy and so commonly used. Again, like in your university math courses, degrees don't really come up that much because radians are just the most commonly used way, okay? That if no unit is given for an angle, it's actually assumed to be in radians. So if you're ever working on a practice question or something and there's no unit given for the angle, that means it's in radians, because we kind of default to radians in the world of math, okay? So how do we convert between radians and degrees? Because again, they're just two different ways of measuring the same thing. We should be able to convert from one to the other, right? Every measure in degrees has an equivalent measure in radians, right? For example, 2 pi radians is the same thing as 360 degrees. So, like, you know how to convert 3 kilometers into meters, right? There's 1,000 meters in each 1 kilometer, so you're going to multiply 3 by 1,000, right? You multiply 3 kilometers by 1,000 meters per kilometer, right? 1,000 meters for every kilometer. To find that, 3 kilometers is 3,000 meters. Those mean the same thing, they're just being measured with a different unit now. 3 kilometers is 3,000 meters, we're just measuring them 2 different ways. Similarly, there are 180 degrees in pi radians. So we can actually use the following conversion factor, the exact same way you would, convert meters to kilometers, since there are pi radians per every 180 degrees. If you want to go from degrees to radians, you could multiply by the pi radians that are in every 180 degrees. Just like you could multiply by the 1,000 meters that are in every 1 kilometer to convert from kilometers to meters, right? Radians to degrees, well, we got to flip that around. We have to multiply by the 180 degrees that are in every pi radians, right? We could always check our make sure, do our unit analysis, make sure the units cancel out the way we want them to. So, for example, if we tried converting 360 into radians, we're taking 360 degrees, we're going to multiply it by our conversion factor. There are pi radians in every 180 degrees. So take 360, multiply it by pi over 180, and again, that unit analysis piece, right? Degrees are going to cancel out, and we'll be left with radians. I'm mentioning that because sometimes students don't take a second to think about it, and they flip this around, and they get a very strange and wrong number, right? And it's because they were kind of just guessing about which one to use and not thinking about, well, what am I trying to convert from and to here, right? What unit do I want to cancel out, and what unit do I want to be left with? And so notice 360 over 180 is 2, right? So we have 2 pi radians. And we know that 360 is 2 pi radians because it would take 2 pi radii to go all the way around the circumference of the circle. It would take 360 degrees to go all the way around the circumference of the circle as well. Those are equivalent measures for the same angle. Okay, let's try out a couple examples here talking about degrees versus radians. So it's asking us to convert each angle to the other way of measuring it. In other words, if it's given in radians, convert to degrees. If it's given in degrees, convert it to rads, and then sketch in standard position. Okay, so more practice with sketching as well. So here we've got 30 degrees. I want to convert it to radians, that means, right? What is the equivalent way of measuring this angle, but in radians instead of degrees? Just like going from meters to kilometers. Okay, same idea, except we're talking angles, not distances. So what do I want to multiply by? I need a conversion factor, right? Meters to kilometers, I would need to, divide by 1,000. Degrees to radians, I need a similar conversion factor, except for the exchange rate between radians and degrees. So I want to convert into radians. So there are pi radians per every 180 degrees. And I can tell I did that right because my degrees are going to cancel out and I'll just be left with radians as my unit, right? So that's a quick way to check our work. So we end up with, this is going to be 30 pi over 180. Again, we could write in that rad symbol, but honestly, a lot of the time, we're just going to leave it out because like I said, when there's no unit, it's assumed to be radians. We're going to be working with radians a lot, so often we just end up leaving them out. Now we just got to think, okay, can I reduce this fraction? Right? This is technically right, but we can probably reduce this to a simpler fraction by checking if both are divisible by something. Right off the bat, I see, well, 30 is just 1/6 of 180, right? These are both divisible by 30, so I could divide my numerator by 30 and my denominator by 30 and see that this is actually just pi over 6, right? 1 over 6 pi, because 30 over 180 is the same as 1 over 6. So 30 degrees is the same as pi over 6 radians. Okay, so if we think about that, what are our quadrantal angles? Well, we've got 0 degrees, but also 0 radians, right? We've got 90 degrees, but also pi over 2 radians, right? 1/4 of 2 pi. We've got 180 degrees, but also pi radians, right? Half of a full circle, half of 2 pi. we've got 270 degrees, 3/4 of a full circle, but also 3 pi over 2 radians. Okay, and 0 degrees or 360, yes, but also 0 radians or 2 pi radians. So we've got 0, pi over 2, pi, 1.5 pi, right? 3 pi over 2, and then 2 pi. Okay, so helpful to start thinking about radians to get used to them. So we want to do pi over 6. Let's think about that. Okay, pi over 6, 1/6 of pi. This is where you're going to get your fraction practice in for sure if you're a little rusty on fractions, right? Think about it. This is half of a pi. We want to do 1/6 of a pi, right? So we're definitely not getting to pi over 2, right? Helpful sometimes too, if you like, to convert this to like an equivalent fraction. Like we could say that this is pi over 2, but we could also think of it as 3 pi over 6, right? 3/6 is the same as 1/2. So we don't want 3/6 pi, we want 1/6 pi. So we're about a third of the way there as we sketch out our angle. Okay, this is 30 degrees, but it's also pi over 6. Okay, again, pi over 2 you could think of as 3 pi over 6. Another way to think about it is that we are, maybe an easier way too, is that we are 1/6 of the way to pi, right? We're 1/6 pi of a rotation. Well, pi is 180. Pi is over here. We're only 1/6 of the way there. So we're definitely not to our pi over 2 or 90. Okay, 2 pi over 3 rads. So this is 2/3 of pi. I'm going to encourage you to start looking at it that way, right? Think about it. 0, pi over 2. We know pi is 180. And this is the power of radians, right? When students don't like the radians, I find they're not thinking about the fact that it's telling you the fraction of the way you are to pi or to 2 pi, right? We are 2/3 of the way to pi. So think about it. Pi would be that rotation angle. We're about 2/3 of the way there. Okay. Now, it wanted us to convert this to degrees, but we can already, right off the bat, we will convert it to degrees, but just to gain some comfort with radians, right, we're expecting to be about 2/3 of the way to pi. You could even use that fact to make a prediction about what this will be in degrees, remembering that 180 is pi in degrees to radians. So what's 2/3 of 180? Okay, hold on to that prediction. Let's see. So 2 pi over 3. If I use my conversion factor here, I want to go from radians into degrees. So doing a quick check to think about this, right, I want to divide by pi radians. That'll make my units work out the way I want. I'll get rid of these radians, and there are 180 degrees in every pi radians. So I'm going to multiply by 180 per pi, right? 180 over pi. Our units are canceling out the way we would like, and we get that this is 2. Oh, and sorry, the pi's also cancel out as well. Here, I'll just write it all out. We get 2 times 180 is 360 pi over 3. That 3 is still down here in our denominator. And then we still had this pi. That's what I was saying, is we could cancel out that pi. It's this many degrees, whatever that is. So pi over pi cancels out. And hey, 360 over 3 is just 120 degrees. Remember what I said, right? 2/3 of pi. So we're saying we're 2/3 of the way to pi. Well, 120 is 2/3 of the way to 180, right? 60, 120, 180. So it checks out. So sure enough, this angle is 120 degrees, or 2/3 of pi, 2 pi over 3. Okay, alrighty. So go ahead and try these ones out. This is just getting practice, or getting comfortable with the idea of converting between those units. As always, right? Pause the video, try them out. I know it just suggests 3a and 4a for now, but you can always take a longer pause, do some more practice with it. Probably with this radian degree stuff, that's a good idea to get comfortable with those radians, because I know they are completely new and we'll be using them a lot. But at least try these ones while it's fresh in your brain. and then we'll move on to a review of reference angles. All right, so these angles in standard position, they're great, but we can't just sit here drawing little spirals all day. We ultimately need to start thinking about like triangles in order to actually be doing trigonometry, right? To actually be doing SOHCAHTOA and all the stuff you know and love for trigonometry, okay, and solving problems with that stuff. So every angle in standard position has what we call a reference angle. It's this reference angle that we're going to use to kind of think of as an angle inside of a reference triangle. We'll get to that in a sec, okay? But that triangle, trigonometry involves triangles. We're going to use that reference angle to think about, okay, yes, I know this angle is part of a bigger picture. It's part of a rotation angle along the Cartesian plane, but we can still kind of use it to build a little triangle to do some math with and think about in order to then place it into the larger context of the full rotation. Okay, so we'll take a look at some here in a second, but just some rules about reference angles. Again, these really are convention, meaning that like mathematicians and scientists have kind of agreed we'll always do them this way so that we can always agree on our work when we, check each other's work and when we try to communicate these ideas. If we all kind of use the same rules, then we won't confuse each other and we'll always know what we mean, and it becomes easier to communicate and write out the math for it. Okay, so reference angles are always drawn between the terminal arm and the x-axis. Okay, that's kind of one of the rules. We're always going to do it referenced to the x-axis. Why not the y-axis? That's one of those things where we just said, hey, let's just reference to the x-axis. That way we're all consistent. And when I say it has a reference angle of 30 degrees, we all picture the same thing and we don't, get different answers, because that would be bad and confusing. So it's either the positive or the negative x-axis, of course, whichever is closer. We're always just going to be making a less than 90 degree angle here, which brings me to the next point. A reference angle is always acute. It's between 0 and 90 degrees, or now that we know radians, we could say it's between 0 and pi over 2. That doesn't mean it's in the first quadrant. It just means the angle we draw in as our reference angle, just to show you what I mean, right? The angle we use as the reference angle is always an angle that's less than 90. You can see for all of these, the angle itself might be larger than 90, but we're going to draw in a little reference angle. Again, why? Because where we're headed with this is to make reference triangles out of them like this that we can then do trigonometry with, okay? And again, going back to that first point, notice they're all referenced to the x-axis. Positive x-axis if that's closer, negative x-axis if that's closer. Okay, reference angles are always positive. We're not really thinking about these as rotation angles so much. What we're thinking of them as is being as part of a triangle, right? What we're essentially trying to do is create a Math 10 trigonometry problem where we're just SOHCAHTOing a good old right angle triangle. Right angle triangles don't really have negative angles in them, so they're always positive. If we need to, think about negatives, we'll do that bigger picture, but for the purpose of getting a reference angle, it's always going to be positive, and we give them the label theta r. You can probably guess why. R is for reference, okay? So the purpose of a reference angle is to, again, use it as a reference. It kind of lets us get our bearings and come up with a reference triangle that we can actually do trigonometry with, which is going to be coming up soon. We'll actually start talking about ratios and trigonometric equations and all that fun stuff in the next lessons. Okay, so just a quick reminder of what reference angles look like. How do you calculate them, right? So in the first quadrant, the reference angle is actually going to always have the same value as the angle itself, right? Starting from there, I rotate to there, and then I draw in a reference angle from my terminal arm to my x-axis, and well, that's just the angle itself that I just drew, right? So in the first quadrant, our reference angle, I'll do it in red because it's given red here, it just is the angle theta, right? They're the same thing. Quadrant 2, though, things get a little bit more interesting because now I've rotated past 90. So to start thinking about a triangle that I could do some trigonometry with, right? If I knew this angle here, I could start thinking about SOHCAHTOA and all that good stuff. Okay, so that's the point here, right? So doing this one here, let's see if we can figure out how to figure out what this reference angle would be. I know we don't know the angle, so we're not going to be able to get an actual number, but if we did, how could we figure out this reference angle? Well, we know that this is 180 degrees, right? Or pi radians. This is 180 or pi radians. So think about that. Well, did we get all the way to 180 with our angle? Just this angle here? No, right? We stopped short of it. We stopped this far short of it. So the reference angle is going to be, right, whatever's left after we take away, look at this here, right? If I take this part away from 180, take this part away, what am I left with? I'm just left with my reference angle. So the reference angle will just be 180 minus the angle itself, the rotation angle itself. Or in radians, the reference angle is pi minus the angle in radians. All right, similar logic holds up in quadrant 3. Sometimes students treat these as like rules to be memorized. I mean, you might accidentally memorize them, but honestly, I find it much easier and better way of understanding to like just think about the relationships here, right? That way you don't have to memorize anything. In quadrant 3, for example, we're going to 180 and then we're going past it by the reference angle, right? We're going past it by the reference angle. So we take our angle, go all the way to 180, and then we go past it. Okay, how far past it? Well, that's going to be our reference angle. Again, referenced to the x-axis so that we can make a triangle like this. And if we knew our reference angle here, we could start doing some trigonometry, some SOHCAHTOA. Okay, so how do I figure out what that reference angle is? Well, kind of reversed here now. If I took the angle itself and I subtracted off this part here, well, that's just 180. So take the angle and subtract 180. The reference angle here will be the angle subtract 180 degrees, right? Again, look at the full angle here, and then imagine taking away 180 degrees, and what would you be left with? You'd be left with your reference angle, okay? What would that same kind of rule, so to speak, it's really not a rule, it's just a relationship, but what would it be in radians? It'd be the angle minus pi. Okay, last one, quadrant 4. Again, we can just kind of think about it. This is not stuff to be memorized, right? If you can understand it, then it doesn't matter if you forget it, because you can kind of just think about it again and you're good to go. So for this one, 180 is not going to be that helpful here because we're going past 180 and then we're also going past 270. So I'll give you a second to think about it. How could we figure, if we knew this angle, how could we figure out our reference angle? Well, we're going not all the way to 360. We're stopping a little bit short of a full 360, right? There's 360 or 2 pi. Okay, so let's think about that. How do I figure out just this part? Well, if I took a full 360 and I subtracted off this, what I'd be left with is just the reference angle, right? Again, imagine taking the full 360 and subtracting away the angle theta. You'd be left with that reference angle. So our reference angle here is going to be, take the full 360 and subtract the angle. Or in radians, 2 pi. Subtract your angle. Okay, so quick little reminder of reference angles. Sometimes it goes the other way too. Sometimes you have the reference angle and you want the angle itself. It's a similar process of thinking about, okay, how is that related to 180 or 360 or whatever it might be based on the quadrant you're in. Okay, let's try out some examples. So for this first one here, it wants us to draw an angle in each quadrant with a reference angle of pi over 4. And then find the measure of each angle in standard position. Okay, well, let's just do that first. Let's actually just draw the terminal arm such that the reference angle would be pi over 4. So I'm just going to do that first. I'm just going to say, okay, in quadrant 1, a reference angle of pi over 4 would look like this. Actually, pi over 4 is 45 degrees. Do you see how I'm figuring that out? Because pi over 2 would be 90. So a quarter of the way, a quarter of the way to pi, right? Or halfway to 90, halfway to pi over 2 would be pi over 4. Half of a half pi. Okay, so this would have a reference angle of pi over 4. maybe I'll put it inside just to give ourselves some, actually no. Actually, yeah, pi over 4. Okay, in quadrant 2, let's draw a terminal arm for an angle that would have a reference angle of pi over 4. Something like that. Okay, see what I mean? Always referenced to the x-axis. In quadrant 3, if this is pi over 4, then that angle has a reference angle of pi over 4. And in quadrant 4, this angle would be pi over 4 for it to have a reference angle of pi over 4. Okay, now let's actually think about what those angles themselves would be. Try to use some different colors. So let's do the quadrant 1, 1 first. That's a nice and easy one every time because we're starting from 0. We're rotating until we hit the terminal arm. So what angle did I just rotate through? Well, pi over 4, right? In that case, theta is theta r. They're the same thing. We're in quadrant 1. So the angle is just pi over 4. Okay, not so simple, but still not too bad. Once we get to quadrant 2, still starting from the positive x-axis, from 0, I'm going to rotate till I get to that terminal arm. And now we got to do a little more thinking. Okay, so let's draw in our quadrantal angles here. We got 0, 90, or pi over 2, 180, or pi, 270, or 3 pi over 2, right? 1.5 pi, and then 0 or 2 pi. So thinking about it this way, right? Now look, I didn't get all the way to pi. I stopped pi over 4 short of pi, right? So how can I figure out my angle itself, the blue part here? Well, I didn't do a full pi. I did pi minus pi over 4, right? So pi minus that pi over 4 there, right? For quadrant 2. So if you want to get a common denominator, you can, right? Pi is 4 pi over 4, 1 pi, minus pi over 4, showing us that this angle here is 3 pi over 4, 3/4 of a pi, right? 3/4 of the way to pi, or 180 degrees. Okay, makes sense. We stopped 1/4 short of getting a full pi, so we're 3/4 of the way to pi. So that is our angle in quadrant 2. Let's move on to quadrant 3. What color should I use? How about yellow? I hope that shows up okay. I'm going to go past pi all the way to the terminal arm of this third quadrant angle now. Okay, and let's think about how to figure that one out. Well, that angle, we went past pi now, right? How far past pi did we go? Well, we went another pi over 4 degrees, or not degrees, sorry, another pi over 4 radians. So we went 2 pi, that's TO pi, not TWO pi. We went 2 pi, and then we went another pi over 4 degrees. Oh my goodness, not degrees, radians. Why do I keep saying degrees? Okay, so do you see how that's our angle? Theta for the yellow one here in quadrant 3, right? Pi plus another pi over 4. So if we want to get a common denominator, we could. Pi with a denominator of 4 would just be 4 pi over 4. Plus another pi over 4. This makes sense. We're going to get 5 pi over 4 radians, right? Past 4 over 4 pi by 1 pi over 4, right? Past 4/4 by 1/4, giving us 5/4 pi. Okay, last one here, maybe red. So I'm going to go even further now. I'm going to go past pi over 2, past pi, even past 3 pi over 2 to the terminal arm of this angle. And so to figure out what that angle is, we're going to have to do, okay, well, let's think about it. I did not go a full 2 pi, right? I didn't go a full 2 pi. How short did I stop? Right, I stopped pi over 4 short of a full 2 pi. So let's take 2 pi, right? That would have been a full rotation, and subtract off what we were missing, what we didn't do. We didn't do pi over 4 of it. And therefore our angle theta, well, 2 pi, if you'd like a common denominator, 2 pi is 8 pi over 4, right? Multiply by 4 over 4 to get a common denominator. 8 pi over 4 minus pi over 4 shows us that we have 7 pi over 4, which once again makes sense because we know we stopped 1/4 short of 8 pi over 4, right? Which is 2 pi. 8 pi over 4 would be 2 pi, and we stopped 1 over 4 pi short of that. So we did 7 over 4 pi, okay? 7/4 of pi rotation. And there we go. Let's try these ones out. So it wants us to determine the reference angle for 4 pi over 3. Again, let's try thinking about this in radians. I know it's tempting to just convert it to degrees, and you can. I'm not saying you can't convert it to degrees, but put in some time and effort with radians because they are worth getting used to. They make trigonometry a lot easier once you're comfortable with them. And yeah, you don't want to be scared of them or anything. So let's try doing this in radians. Okay, we've got 0, pi over 2. Plus, honestly, converting them just makes extra work. If you can just get comfortable with them, then when you're given radians, you can just work with them the same way you're comfortable working with degrees. Okay, you don't have to waste time converting back and forth. Plus, the fractions work out nicer with radians than they do with degrees. So we want to determine the reference angle for 4 pi over 3. I want you to think about this. This is kind of one of those questions I ask myself when I'm working in radians. One of the first ways to kind of get my bearings. Is this more than 1 pi or less than 1 pi? Well, it's 4/3 of pi, right? 3/3 of pi would be 1 pi, and we've got 4/3. Think about it like pizza. There are 3/3 of a pizza, making 1 full pizza. If you've got another third, you've got more than 1 pizza, right? 4/3. So we've gone past pi. Now, how far have we gone past pi? Just let me draw pi first, right? There's 3/3 of pi, or 1 pi. We've done 4/3 of pi. So we've gone past pi by another 1/3 of pi, which kind of lets me already figure out my reference angle, right? That's not the best sketch in the world, but what would this angle be, right? If stopping right there is 3/3 of pi, and this is 4/3, what's this? This must just be 1/3 of pi, right? We went 1/3 of pi past pi in radians. So we can do the math here, but see what I mean? If we can start thinking about it too, it becomes a little more intuitive. So that reference angle must be 1/3 of pi. Let's kind of prove it with our math here. I typically use green for reference angles, so I'll try to be consistent. So it's asking us to determine our reference angle. Well, the reference angle is going to be, okay, pi. Sorry, I'm mixing up my things here. I'm thinking of finding the angle itself. We want to find the reference angle in this case. So we want to do 4 pi over 3, which is the full angle. 4 pi over 3, okay? And we want to figure out just the reference angle there in green. So essentially we want to take away this part. Well, what is that part? Yeah, that's just pi, right? This would just be pi. So 4 pi over 3 minus pi. If you want to get a common denominator, you can. That just means we've got 4 pi over 3 minus 3/3 of pi, right? Minus 3 over 3 pi. Okay, and 4 minus 3 is 1. So like we predicted, our reference angle here is just 1/3 of pi. 1/3 pi. Or 1 pi over 3, or I guess just pi over 3. Okay, but see what I mean? We can kind of think about it. If we get comfortable with fractions and with radians, we've gone past 1 pi, past 3/3, by how much? Well, by 1/3, right? To give us 4/3 total as our angle. Okay, let's try this one. An angle lies in the 4th quadrant and has a reference angle of pi over 6. What is the angle in degrees? Okay, so they're throwing in a conversion for us here too. Okay, so let's start thinking about this. We're in the 4th quadrant. Okay, so we are in somewhere in quadrant 4. So my terminal arm is somewhere like this. It's probably not accurate in terms of what the angle actually looks like, but it's good enough. It's in the right quadrant, okay? It has a reference angle of pi over 6. So this angle here, reference to the x-axis, is pi over 6. Well, let's think about this now, right? We've got 0 or 2 pi. We've got, 0 or 2 pi. Then we've got pi over 2, right? This is pi, so halfway to pi would be pi over 2. And then halfway to 2 pi would be 1.5 pi, right? 3 halves pi, okay? So how do we figure out what this what this angle is if this part here, the reference angle, is pi over 6? Well, I mean, again, think about the relationships. Did we do a full circle? Did we do a full 2 pi? No, we stopped short of it, right? We did 2 pi. How far short did we stop? Pi over 6, right? And that will be our angle. Take a full rotation and just subtract off this part, and you're left with the angle itself. So that means theta is, again, you can get a common denominator if you like. 2 pi will be 12 pi over 6, multiplying by 2 over 2. Subtract 1 pi over 6, and we get that the angle is 11 pi over 6. Once again, makes sense. We know 12 pi over 6 would be a full 2 pi, and we've stopped 1/6 short of that. 1/6 of pi short of that. So we should have gone 11/6. Not a full 12/6 to get 2 pi, but 11/6 to be 1/6 pi short of a full 2 pi. Okay, now it wanted us to convert it to degrees. So we know how to do that. We can take our 11 pi over 6, which is in radians. And how do we go to degrees? Well, we know there's 180 degrees in every pi radians. I want to cancel out my radians, so I'll put them down here. Okay, and then we can see we'll be left with degrees, and the radians will cancel out because we have radians divided by radians. And so we're going to get 11 times 180 over 6. And then the pi's we can see will just cancel out, so we don't need to worry about those. So 11 times 180 over 6 might not be the most intuitive calculation, but 11 times 180 is 1,980 over 6. And if you divide those, you'll actually get that this is just 330 degrees. Okay, actually makes a ton of sense because we know that pi over 6 is 30 degrees, right? If you're saying, I didn't know that, well, think about it. It's 1/6 of pi, and pi radians is 180 degrees. So what angle in degrees is 1/6 of 180? 30 degrees, right? It takes 6 30s to make a 180. So what we're saying here is that we are pi over 6, or 30 degrees short of 360. So 330 is 30 degrees short of 360, right? It checks out, okay? And just as a side note, could you have done this? Could you have taken, I mean, for both of these really, could you have taken 4 pi over 3 and right off the bat multiplied it to 180 over pi, multiplied it by 180 over pi, and done this whole question in degrees? Sure, you could. And some students, they do that, but they end up making so much more work for themselves in the long run, and they make the fractions like not work out nicely and just like simply can't simplify nicely. And then they end up saying, oh, I got these ugly numbers that I don't know what to do with. And it's because they're kind of forcing themselves to always work in degrees, when degrees often are not the best way to approach these angles, okay? So do take some time to be uncomfortable with radians and work through them and gain that comfort. I know it's often easier to just go with the thing we're comfortable with at first, but putting in that putting in the effort to get comfortable with them does pay off in the long run. It's worth it. Okay, not saying you can't use degrees, but and you will use degrees still, don't get me wrong, but it's worth taking some time to get comfortable with radians and not just saying, I prefer degrees, I'm not even going to bother learning about those. Never going to use them, okay? They're very handy to use. We will use them a lot, promise. Okay, let's try these ones out. It wants us to sketch these angles and find their reference angles. So this one's given to us in degrees, so we'll work in degrees. like I said, we can work in whatever they give us. That's fine. It's not like we have to convert to radians. All I'm saying is don't be scared of radians, right? Work with them when you can, and you'll find that they become handier and handier over time. Okay, so 750. This is actually one that goes beyond 360, right? As we saw, there's nothing wrong with that. No one said we had to stop at 360. We can keep rotating. So there's a full 360. Oh boy. That would be 540, right? 360 plus 180. That would be 720, 2 full rotations, right? 360 times 2. Now, how much further do I have left to go until I'm done? 30 more degrees, right, to get to 750. There we go. So 30 more degrees, that's 750 degree rotation. Our terminal arm is still there. It's just done 2 full rotations now, okay? So that's a full 750. We want to figure out what is the reference angle, theta r, right? Again, so that we could eventually, this is where we're headed, build a triangle and do some trig with it, okay? Well, I mean, one way to look at this is just to start subtracting off rotations until you get to just a nice angle that's easier to work with, right? Get to what we call a principal angle. Principal angles are just the ones from 0 to 360. They don't involve like multiple rotations. But again, like we could just notice here, what do we need to take away to figure out that reference angle? Well, we just got to take away all this stuff and we'd be left with our reference angle. So what is that? What did I just scribble out? I just scribbled out a full 2 rotations, right? So we can kind of see that our reference angle is just going to be, we need to take 750, that orange angle, our overall angle, whoop, cat is meowing, and subtract off the 2 full rotations we did before, and we can see that our reference angle is 30 degrees, which checks out because remember what we said. We're going to go a full 360 and then 720, and then we've got 30 more degrees to go to get to 750. So that makes a ton of sense that this would be 30 degrees. So notice the fact that it's more than 360 doesn't change anything about the reference angle. Still reference to the closest x-axis, still positive, right? Still between 0 and 90, all that good stuff. And again, because the whole point is to eventually build a nice little right angle triangle that we can do trig with. Okay. Let's try doing the same thing for 10 pi over 3. And again, I'm going to encourage you, let's challenge ourselves here to work in radians. It's new, but we can handle new things. We can figure out and get comfortable with them, okay? So could we convert it to degrees and do this whole thing in degrees and then convert back to radians at the end? Yeah, but why make extra work for us forever when we can put in a little work now and just be comfortable with radians always, okay? So 10 pi over 3, let's think about this. Well, what we know a full rotation is 2 pi. What would 2 pi be as like a fraction over 3? Right? This is 0 or 2 pi. How could we express 2 pi but as like a fraction with a denominator of 3? Well, it's 6 pi over 3. Sorry. Yeah, no, that's right. 6 pi over 3, right? That would be 2 pi as a fraction over 3. So we've gone past 2 pi. We're at 10 pi over 3. Right? This is pi, but we could also think of it as 3 pi, right? We go past 2 pi. If we do another pi, that's now 3 pi. Okay? And if we like, we can kind of think about 3 pi as 9 pi over 3. So we've even gone past that, right? We've done, let's just start drawing this out. We've done 2 pi, or 6/3 of pi. Then we've done another pi, or another 3/3 of pi, to give us a total now of 6 plus 3 is 9/3 of pi. And then we've gone another 1/3 pi to get to 10/3 pi. Right? 10/3, that's 3 1/3 pies. 3 1/3 pizza. If you have 10/3, you've got 3 full pizzas and then another third of a pizza. Okay? So take a look here. Can kind of, based on what we just said, you can probably work out what this reference angle is going to be, right? If we think about this stuff, rather than being math robots, it actually makes it a lot easier, okay? So what's that reference angle going to be? It's going to be, I'm predicting, 1/3 pi, right? Because we said 6/3, 9/3, and then another 1/3 of pi to get 10/3 of pi total. We can show that with the math here as well. Let's say we have 10/3 pi, 10 pi over 3. If we take away all this stuff, we'll be left with the reference angle. And that is 1.5 full rotations, right? It's 2 pi and then another full pi, so 3 pi. 10 pi over 3 minus 3 pi is our reference angle. Okay, again, getting a common denominator if we like, that's 10 pi over 3 minus 3 pi could be rewritten as 9 over 3 pi, 9/3. And therefore our reference angle, 10 minus 9, is, like we predicted, 1/3 of pi, right? We went 1/3 of pi past 9/3 of pi. So that's our reference angle. All right. All right, so they've come up a couple times, but let's officially talk about them now here. These coterminal angles, okay? And like the name kind of suggests, well, you know what? I won't spoil it. Let's just do this investigation here. So on the Cartesian plane below, it wants us to sketch angles of 20 degrees, 380 degrees, and 740 degrees. So let's think about this. We got our 0, our 90, our 180, our 270, working in degrees because they told me to work in degrees basically by giving me them in degrees, and our 360 would be all the way around, okay? So here we go. Let's do 20 first. So 20 would look like, well, starting from 0, I'm going to go 20 degrees. That was pretty quick. There would be the terminal arm for that angle. That's a 20-degree angle. I'll color code it in orange there. Now we want to do 360. I'm going to use a different color. How about blue? Okay, so I'm going to go, sorry, not 360, 380. I'm going to go all the way to 360. And then how far do I have left to go? I just have another 20 degrees to get to 380, don't I? So that angle's terminal arm is going to be in the same spot as the 20-degree angle's terminal arm, right? Starting from 0 and going 20 degrees counterclockwise gets you to the same place as starting from 0, going all the way around, and then going 20 degrees. Because you're essentially starting back at 0, then going 20 more. Let's move on to 740 and see what we see here. So now what are we going to do? We're going to go past 360. Okay, we still got to do another full rotation, another full 360, and that would bring us to 720. And now how far do we have to go to get to 740 from 720? Hey, another 20 degrees, right? So that angle's terminal arm would also be in the same place. Can you see why we might call these angles coterminal? They're not the same angle, but their properties, their coterminal arms, their reference angles, as we'll see eventually, their trigonometric angle, the ratios are all going to be the same. So they have a lot in common because at the end of the day, they kind of end in the same spot. They give us that same terminal arm. They're coterminal, giving them the same reference angle and therefore the same reference triangles and therefore the same trigonometric ratios. Okay, so if two angles have the same terminal arm like these three angles did, they are said to be coterminal. Okay, this means they're going to have the same reference angles as well as the same reference triangles, and as we'll eventually see, the same trigonometric ratios. So sine of 20 will be the same as sine of 380, which will be the same as sine of 740, for example. Because they all have the same reference angle, they all have the same reference triangle, and therefore they all have the same, opposite over hypotenuse, or adjacent over hypotenuse, or opposite over adjacent, okay? So how can we find a coterminal angle? Let's think about that. What did we have to do to go from 20 to 380? Well, we just had to go to, we had to do another full rotation, right? How did we get from 380 to 740? Added in another full rotation, right? 2 full rotations counting from 20 gets us to 740, okay? So that's how we can find any coterminal angle. We can add or subtract multiples of 360 degrees or 2 pi radians, because that's just a full circle. from any angle in standard position. And that makes a lot of sense, right? Because I mean, think about it. If you're facing, if you're facing some object in your room and you do a full circle, you're going to be back to where you started. You're going to be facing that same object again, right? If you do 10 full circles, you're going to be facing that same object again. Every time you do a full circle, you end up back where you started, right? So each rotation of 360 or 2 pi in either direction, whether it's positive or negative, represents a full circle around. So adding or subtracting 360 from an angle is always going to give you an angle that is coterminal to that angle, okay? So rotating a full 360 or a full 720 or a full 1080, any multiple of 360, we're going to end up right back where we began, right? So that goes for any multiple of 360 or 2 pi, right? I mean, we kind of saw that with these examples here. We had to figure out what was the, coterminal angle there, we subtracted 3 pi, right? Or here, I guess, sorry. We subtracted the 720 to kind of think about what would be a coterminal angle, in this case, my reference angle, okay? So again, if we do 2 full circles, 3 full circles, or 100 full circles, we always end up back where we started. So in general, the coterminal angles for any angle theta can be found like this. Sorry about that. Okay, take your angle and add some multiple of 360. So theta plus 360n, where n is just an element of the integers. So remember, the integers are the whole numbers, but including negatives too. So like -3, -2, -1, 0, 1, 2, 3, but not like 2.5 or 1/2, right? The whole numbers, but including negatives, that gives us the integers, okay? So where n is just an element of the integers, that's how you can find theta. Add any multiple of 360. Again, since it's integers, that could mean subtract any multiple of 362, right? N could be negative, right? Or add multiples of 2 pi, because that just means you're doing full circles and you're going to get back to where you started, a coterminal angle. So for this reason, every angle actually has infinite coterminal angles, right? You could add 1 billion times 2 pi, and that would give you yet another coterminal angle. There's no place we ever have to stop. So 2 ways we can deal with this. Later in the trigonometry unit, we'll see what's called a general solution. That means, there's a way to talk about all possible angles that could solve it. It looks a lot like this kind of thing, where we add multiples of 2 pi or multiples of 360. The other thing we sometimes see is that we often see the domain of the angle limited when we are asked to find coterminal angles. So for example, there are infinitely many angles that are coterminal to 45 degrees, right? We could just keep adding 360s or subtracting 360s forever and ever and ever and find more and more angles that are coterminal to 45. But if our domain has been limited, so if we limit the domain for theta, and it is a domain because theta is often our independent variable here, our standing in for x kinda, okay? If we limit the domain for theta from 0 to 720 degrees, there's only one coterminal angle, 405, right? You could take 45 and add 360 to get 405, but if you add another 360, you're gonna be up at up in the 800s, and you're going to have gone beyond 720, right? So yes, it has infinitely many coterminal angles, but for this domain from 0 to 720, there's just one, 405 degrees, right? The next coterminal angle to 45 degrees would be beyond our domain because it would be beyond 720. 405 plus 360 goes past 720. Okay, let's try this out. So it says for each angle, state 2 positive and 2 negative coterminal angles. Again, negative angles can be coterminal, right? You could have something like this, and you could say, okay, I'm going to do a full 360 this way in the clockwise direction. That is a negative coterminal angle, okay? But let's just, there's literally infinite ones we could come up with, right? Let's just do the first 2. We could do, right, anything that is 270 degrees plus 360n will be coterminal. So let's make n 1, right? Let's do 270 plus 360. N is 1. Okay, 270 plus 360 gives us 630 degrees. That will be coterminal to 270, right? Quick proof. This is 270, we know, right? It's the negative y-axis. So that would be 270 degrees. If I do 630, that's going to go past 270 to 360. And then I need to do another 270, so I end up in the same spot. Okay, coterminal. What's the next smallest one we could get? Well, we could add two 360s, right? Do two full extra spins. So 270 plus 720 to get 990 degrees. And we literally could do this for the rest of our lives. We could just sit here and come up with more angles that are coterminal to 270. We would literally never run out of answers, right? Our domain isn't limited here. But it said to come up with two, and there we go, we did. Now it wants us to find two negative coterminal angles. So let's see if we can do that. How could we? Well, how about subtracting 360s, right? Starting from 270 and rotating a full circle clockwise is still going to get us back to where we started. So negative rotations give us coterminal angles as well if we do a full rotation. And 270 minus 360 is negative 90 degrees. Hey, that makes a ton of sense, right? Negative 90 will be coterminal. Start from 0 and go 90 degrees clockwise, and sure enough, where you end up? You end up at where we think of positive 270 being. So that is a coterminal angle to 270. Okay, next one, you can probably guess where my head's going, but this is not the only one we could do next. We could do 270 minus 720, right? That's going to give us negative 450. Makes sense. Do a negative 360, then do another negative 90 to get to negative 450. And you'll be back to where you started with the 270. So negative 450 is coterminal to 270. All right, another one here just using radians, but don't have to be scared of radians, right? What will be coterminal to this? Well, anything that's separated from it by a full rotation, by a full 2 pi. Okay, so we just need to take negative pi over 4 and add integer multiples of 2 pi. So n is an integer. Okay, so here we go. Let's do, how about negative 5 pi over 4 plus just one full rotation, plus 2 pi. Okay, if you want to get a common denominator, you can, right? 2 pi is equivalent to 8 over 4 pi, right? If we want to write it with a denominator of 4. So negative 5 pi over 4 plus 8 pi over 4, and negative 5 plus 8 is 3 pi over 4. That is coterminal to negative 5 pi over 4. Okay, again, does make sense when we think about it. Negative 5 pi over 4, so we're going to do negative pi, and then another quarter of pi. That's negative 5 pi over 4. Okay, or we could go in the positive direction, 3/4 of the way to pi. 3/4 pi, right? They're coterminal. Coterminal. The terminal arm is in the same spot. All right, let's do the next one. Wanted 2 positive and 2 negative. So let's do negative 5 pi over 4 plus 2 pi's, right? 2 full rotations, so plus 4 pi. That's going to be negative 5 pi over 4. If we get a common denominator, 4 is the same as 16 over 4. Right? Multiply by 4 over 4. So negative 5 plus 16 is 11 pi over 4. And that angle will be coterminal. Very similar situation to this one, except we do another 8 pi over 4. We do another full rotation, and we get back to there. All right, let's find two negative coterminal angles. So now, instead of adding a 2 pi, how about we subtract 2 pi? Do a full rotation in the negative direction. Negative 5 pi over 4 minus 2 pi, well, that's negative 5 pi over 4 minus 8 pi over 4. Negative 5 minus 8 is negative 13 pi over 4. One more, negative 5 pi over 4 minus 2 full rotations. So 2 full rotations in the negative direction. That's going to give us negative 5 pi over 4 minus 16 pi over 4. Negative 5 minus 16 is negative 21 pi over 4. And that is coterminal to negative 5/4 pi, right? And we could do this all day, like I said. There's literally infinitely many, especially since they haven't limited our domain here, okay? All right, So go ahead and try this one out. Now this one does limit the domain. So this is giving you some practice with the idea of, okay, I'm gonna find coterminal angles, but I can only go until, the next one would put me beyond our domain, whether that's above or below. This one gives us a negative, lower bound on our domain. So that'll get you thinking as well. Try those out. As always, might be a good idea to pause and try a couple more as well until you're feeling comfortable and ready to come back and finish up this lesson actually with arc length. But try that one out first. All right, so arc length is actually a topic that kind of came up when we were first defining the radian, okay? You'll see a lot of familiar terminology here from when we were talking about the radian, okay? So what is an arc? An arc is just the distance, whoa, I don't know what happened there. It's just the distance that an angle subtends. What does subtends mean? It's the distance along the edge of the circle that if you rotated through that angle, the angle kind of sweeps along, right? I think of it like if you were going to rotate through this angle and you were holding a paintbrush, how long would you have painted, right? So this here is the arc length associated with this angle, right? Because to rotate that angle out, we're subtending that arc along the circumference of the circle. So it's the length on the circle's circumference that the angle kind of sweeps through, okay? So obviously, as the angle gets larger, the arc length is going to get larger, right? If I were to draw, this angle, call it phi, that's another Greek letter we often use to represent angles, that obviously has a bigger arc length than that smaller theta that's drawn in there, okay? So as theta gets larger, the arc length that we're subtending gets larger. As it gets smaller, the arc length that we're subtending gets smaller. And so it's actually the definition of the radian that gives us a formula. So it's not like no formula is just magic. It comes from relationships and stuff like this. But this formula actually just comes straight from thinking about the definition of the radian. So it gives us a formula for finding the arc length of any angle as long as that angle is in radians. And you'll see why when we, talk about it and think about the definition of the radian. Okay, so we must, you got to say it to yourself 3 times so you don't forget right now, okay? To use this formula, which is on your formula sheet, the angle must be in radians. That is not an option. It just doesn't even make sense and it won't work for reasons that you'll see when we talk about where it comes from, okay? If you use it in degrees, it just doesn't make sense and it doesn't work at all. So, must be in radians. Okay, but let's talk about where it comes from and why it really is just using the definition of a radian. So remember, what is the definition of 1 radian? It's just the angle that would subtend an arc of 1 radius, right? If this angle is 1 radian, then this arc would be 1 radius long. This length here would be the same as this length here. We can actually kind of tell that this angle is probably a little less than a radian because this arc doesn't look like it's quite as long as this radius here, even if you were to straighten it out, okay? So again, right, there's a radian because this is the same length as the radius, this, okay? So think about that. 1 radian then is just the angle that gives us an arc length of 1 radius, okay? 2 radians. 2 radians would subtend an arc length of 2 radii, right? If I make this angle twice as big, so now this is 2 radians instead of 1, you can see that now we've subtended a total distance. The total arc length now is 2 radii, right? Do you notice how that's gotten about twice as big? There's now 2 radii that fit in there, okay? 3 radians would subtend an arc length of 3 radii, and on and on and on. So we can see then that the number of radians we've subtended is just equal to the arc length over the radius, right? See what I mean? Like if we've done 2, if the arc length is 2 radii, right? if we've done 2 radii, well then we've done 2 radians. So like, again, let's say our arc length is 20 centimeters and the radius of our circle is 10 centimeters. What angle have we gone through? Well, we've subtended an arc that's as big as 2 radii. And by definition, that means we've done 2 radians, right? If we've done 3, if our arc is now 3 radii long, 30 centimeters, the radius of the circle hasn't changed. We've just moved through a bigger arc length, right? And so now we've gone through an angle of 3 radians, and on and on and on. So this is really just using the definition of the radian. How big is your arc in terms of the number of radii, right? Another way to look at this, we're dividing by radii. So how many radii fit into the arc length that's been subtended? And that tells you how many radians you've rotated through. And that is why this angle makes no sense for degrees, right? If you've gone like 20 degrees, that doesn't mean that your arc length is going to be 20 radii. 20 degrees is not very far at all, right? 20 degrees is like that big of a rotation. That is definitely not going to be, that arc there, definitely not as big as the radius. Okay, so that's why this just doesn't work. But because the definition of the radian is based on relating the arc length to the radius, this formula works perfectly when our angle is in radians. Doesn't work at all if it's not. So A is the arc length that's been subtended, R is the radius of the circle, and theta is the central angle in radians. Don't forget, gotta be in radians. So sometimes you're given an angle in degrees for these, and if you're not paying attention, you'll plug it into this formula, okay? So be careful. But no worries, if you are given the angle in degrees, we know how to convert degrees into radians. We can just multiply by pi over 180 because there are pi radians in every 180 degrees. Okay, let's take this equation for a spin with a couple examples and then we are done. So a section of a car windshield is cleaned by a wiper as shown in the diagram to the right. The arm of the wiper is 22 inches. So can you picture this, right? This is like the wiper on a car windshield. It's going E-er, right? It's rotating through an angle. And it rotates through a central angle of 132 degrees. We want to determine the length of the arc that is created by the tip of the wiper to the nearest tenth of an inch. Okay, so the arc, remember, that's the distance traveled along the circumference of the circular path. So this is what we want to figure out. How long is that arc length? Okay, how far have we actually traveled there? Okay, the tip of the wiper. All right, now what is this 22 inches then? In terms of like our formula and in terms of what it represents on, can you picture the circle here? Right, what would that 22 inches be? Yeah, that's just the circle's radius, isn't it? Right, if you imagine rotating that wiper all the way around, wouldn't be good. It would mean your wiper was broken, right? But if it rotated all the way around, it's just making a circle. And that circle will just have a radius of the wiper's length because it's fixed here and it rotates around that point. Okay, now do you see any flags, any red flags here about our angle if we want to use it with this formula? Right. This is our angle, but it's in the wrong units right now. This formula is based on the fact that an angle of 1 radian subtends an arc length of 1 radius. It makes no sense if we're not using our angle in radians. That's not how degrees are set up, right? Degrees aren't based on arc lengths being subtended. Okay, so let's just make sure we don't forget to convert our 132 degrees into radians. Well, there are pi radians in every 180 degrees. You can always quickly do a double check that our units cancel out as expected, but degrees over degrees, those do cancel out. And so we get 132 over 180 pi radians. Could we reduce that fraction? Sure. But since we're getting everything to the nearest tenth of an inch here, honestly, probably just good to we're probably good to just work in a decimal here. So I'm just going to do 132 times pi over 180. Now, what I'm not going to do is do this, 2.3. That is way, way over rounded. We got to be careful about over rounding, okay? This is always true in math, but we don't want to do that because that is really what my calculator actually gave me is this, okay? And it might not seem like a big deal, and it might honestly not be a huge deal here because it's followed by a 0. But what can happen is if you keep rounding in every step and rounding and rounding and rounding, by the time you get to your final answer, you can have over-rounded. And since the diploma just wants your answer sometimes to the nearest hundredth, and the diploma is marked as either right or wrong, right? There's no, like if it's supposed to be 1.22 and you say 1.23, you're just losing that mark, right? So we don't want to over round. I mean, we talk about this in all of your math courses and your science courses as well, but just a reminder, okay, keep your unrounded answer because we don't want to end up over rounding by the end and changing our final answer, okay? So I'm going to use that unrounded number in my future calculations. Anyway, the radius, as we established, is 22 inches. And we want to know what is the arc length. Well, we can use our formula for this, and we're ready to actually use it because we have converted our angle into radians. So the angle is equal to the arc length divided by the radians. Sorry, the radius. Okay, makes sense because a radian is just how many radii fit into that arc length. That's how many radians you've gone through, you've rotated through. Okay, but it's not solved for what we want. What we want to find is what we want to find is A, the arc length. So let's multiply both sides by R to isolate A. And we get that the arc length is just going to be R times our angle theta. So it's just going to be, just going to drop the color coding here. R is 22 inches. And theta, again, I'm going to use that unrounded answer. So 2.303836. And we get that the arc length is, sorry, I just got to quickly calculate. I lost my answer that I had written down. 50.68436 inches. Again, never a bad idea to write down your unrounded answer in case you need it later. Maybe you need it if this question had a part B or something, okay? But in this case, we are done. We just need to now do this to the nearest tenth of an inch. So 50.6, be very careful. You would hate to do all of this right and then lose the mark on the diploma for a rounding mistake, right? The 6 is followed by an 8. So this is 50.7 inches. We got to round up to 7. Because 0.68 is closer to 0.7 than it is to 0.6. So that's the arc length. This is our tip of our wiper blade is moving through an arc of 50.7 inches every time it eats and every time it earns. All right. One more example here, a released diploma question. Let's try it out, and then that is lesson 1 of trig done. So often, like I said, a good idea to read what we call the question stem, the actual question, before you read the source, the information. So the central angle formed when the adult travels 10 meters to the nearest degree is. Okay, so we're looking for an angle when the adult travels 10 meters. Let's read the question, see if we can figure out what's going on. A circular carousel has a diameter. Ooh, careful. Don't let them trick you. There's no diameter in our equation. There's a radius of 22 meters. An adult is standing on the outer edge of the spinning carousel. Okay, so there they are. They're on the outer edge of it, meaning that as this goes around, they're basically doing the biggest possible circle they could, right? If they were standing closer to the center, they'd be completing a smaller circle every time they went around, moving through the same angle, but the actual circumference of the circle that they're on would be smaller. Okay, so let's talk about that diameter problem. Because this, remember, diameter is the whole distance across the circle. We want the radius, which is half of the diameter, right? So if this is the diameter, what's the radius? Well, it's just the diameter over 2, right? Half of the diameter. So 22 meters over 2. So our radius is 11 meters. Okay, crisis averted. We didn't fall for that one. Okay. Now, what are we actually trying to figure out here? We want to figure out the central angle formed when the adult travels 10 meters. So let's look at this from above. Let's think about this from a bird's eye view. Because when the adult travels 10 meters, what does that mean? Well, the adult's not moving like in a straight line, right? They're following this curved circular path. So for them to go 10 meters, it means they're moving, well, in a curve, but 10 meters. In other words, they're going like this, 10 meters. Maybe I should have picked, oh, you know what? I did pick a different color. I picked red. Sorry. Let me try that again. They're moving 10 meters along an arc, right? That's the actual distance the adult is traveling. They're moving along the edge of the circle 10 meters because that's how they're standing. They're on the edge of the carousel and they're going around the circle. So 10 meters is just the arc length they've subtended. What we want to know is what angle would they have to move through to subtend that arc length. In other words, what is this angle? What angle have they rotated through as they moved an actual distance of 10 meters? We now know that the radius is 11 meters. And our angle, well, I think we're ready to find it because theta equals A, right? The total arc length divided by how many radii fit into that arc length. Because again, 1 radian is the angle you move through to subtend an arc length of 1 radius. So that's where this formula comes from. Okay, so for us, that means we have to take 10 meters and divide it by 11 meters. And therefore, our angle theta is just 10 divided by 11, or again, not going to over-round here. I know I'm going to have to do more with this number still, so I'm definitely not going to say 0.9. We don't want our answer to be off. Okay, so it's been 0.909091 radians. Okay, don't get uncomfortable with the fact that there's no pi there, right? Remember, pi is also just a number. It's 3.141592653 or whatever, right? So this is, it's in radians, okay? Pi just shows up because we can think of it as multiples of, fractions of 2 pi because there's 2 pi radians in a full circle. Anyway, that's our angle in radians. Great, that's technically we've answered the question, except it's multiple choice, and they didn't give us options in radians, so we'll need to convert this to degrees and see which one matches ours. Hopefully one of them, or maybe we made a mistake if none of them do. And that would be okay, we'd just double check our work and try again. All right, so there are 180 degrees in every pi radians, just using a conversion factor here. And so I'm going to double check that I did it correctly. The radians cancel out and I will be left with degrees. So I need to take 0.909091, multiply it by 180, divide it by pi. And what that gives me is, when I put that all in my calculator, 52.087 degrees. Okay, so to the nearest degree, like it said, that matches option C. And there we go. There's our answer. Okay, so go ahead and try this one out while this stuff is fresh in your brain. But that's it for lesson 1 of trigonometry. So now you can work on the rest of whatever practice questions you've got left and what you need to work on. And as always, don't be shy to reach out for help or with questions or concerns or book a meeting or whatever you might need to do. I'm always happy to help. But there we go.